January of 2025, a team of physicists in Vienna did something that should have made front-page news around the world. They took a cluster of about 7,000 sodium atoms, bound together into a single nanoparticle, and they fired it through a specially designed interferometer. And what came out the other side was an interference pattern, a wave pattern. The kind of pattern you get when a wave passes through two openings at once and interferes with itself on the other side. Now, 7,000 atoms doesn't sound like much until you think about what that actually means. This nanoparticle had a mass of about 170,000 daltons. That puts it in the same weight class as a small virus. It's an object that, if you scaled it up enough, you could see under a decent microscope. And the Vienna team proved that this object, this thing made of 7,000 atoms, did not travel through the interferometer as a particle. It traveled as a wave. It went through both paths at the same time. It existed in what physicists call a superposition, a state where the nanoparticle was, in some very real sense, in two places at once. But here is what makes the result genuinely unsettling. The moment anyone tried to figure out which path the nanoparticle actually took, the interference pattern vanished. The wave behavior disappeared. The nanoparticle suddenly acted like a normal object traveling through one path, and one path only. The act of looking at it changed what it did. This is the observer effect, and it is not new. Physicists have known about it for nearly a century. They first saw it with single electrons, then with photons, then with atoms, then with molecules of 60 atoms, then 430 atoms, then 2,000 atoms. Every time they push the boundary, the result is the same. Quantum objects exist in superposition until something observes them, and then the superposition collapses into a single definite outcome. The experiment always works. The math always checks out. Quantum mechanics has been confirmed to more than 10 significant figures of accuracy, which is like predicting the distance from New York to Los Angeles and getting it right to within the width of a human hair. So the theory works. Nobody disputes that. What physicists cannot agree on, what they have argued about for 100 years and still cannot resolve, is what the observer effect actually means. What counts as an observation? Why does looking at a quantum system change it? Does the system exist in a definite state before you look? Or does the act of looking somehow create the outcome? Does consciousness play a role? Does reality itself depend on observation? These are not fringe questions being asked by people on the margins of physics. They are published in Nature, in Science, in physical review letters, by researchers at Princeton and MIT and Oxford and Vienna. And yet, for decades, the professional culture of physics made it essentially career suicide to ask them out loud. There was an unwritten rule. You could use quantum mechanics. You could calculate with it. You could build technologies with it. But you were not supposed to ask what it meant. That rule is finally starting to break. But the questions it suppressed are more unsettling than most people realize. Because the observer effect doesn't just raise abstract philosophical puzzles. It carries specific, concrete implications about the nature of consciousness, about whether reality exists when nobody is looking at it, and about whether you have free will. These are implications that many physicists understand perfectly well, but would rather not discuss in public. And when you trace the history of who tried to discuss them and what happened to their careers, you start to understand why the silence lasted as long as it did. This is the story of what the observer effect is actually telling us. Why so many brilliant people spent so long pretending it wasn't, and why the answers we're starting to get might be stranger than anyone expected. To understand why the observer effect is so disturbing, you need to see the experiment that revealed it. And you need to see it not as a textbook diagram, but as what it actually is, which is one of the most profoundly weird things human beings have ever witnessed. In 1801, a British polymath named Thomas Young set up an elegantly simple experiment. He took sunlight, passed it through a tiny pinhole to create a coherent beam, and then directed that beam at a barrier with two narrow slits cut into it. On a screen behind the barrier, he watched what happened, and what happened was an interference pattern, alternating bands of bright and dark. The bright bands appeared where waves from the two slits arrived in sync and reinforced each other. The dark bands appeared where the waves arrived out of sync and cancelled each other out. The result proved that light behaves as a wave. It was a beautiful experiment, and physics world readers voted it the most beautiful experiment in physics 2 centuries later. But the story didn't end there, because in 1959, a German physicist named Klaus Johnson performed the same experiment with electrons. Not light, electrons. Tiny particles of matter, the kind that orbit atomic nuclei, the kind that carry electrical current through wires. And he got the same interference pattern. Electrons, it turned out, also behave as waves. That was strange enough. But the truly mind-bending version came in 1989, when Akira Tonomura at the Hitachi Advanced Research Laboratory in Tokyo performed the experiment with single electrons, fired one at a time. Tonomura used an electron biprism, essentially 2 paths for a single electron to take. He turned the electron source down so low that only 1 electron was in the apparatus at any given moment. There was nothing for it to interfere with. No other particles, no other waves, just 1 electron, alone. The first few electrons landed at seemingly random spots on the detector. After 10 electrons, the pattern looked like noise. After 100, you might start to squint and wonder. But after 10,000 individual electrons, each one fired separately, each one alone in the apparatus, a perfect interference pattern had emerged. Wave crests and troughs, bright bands and dark bands, exactly the pattern you'd expect from 2 waves overlapping. In 2002, readers of Physics World magazine voted Tonomura's experiment the most beautiful experiment in the history of physics. And the beauty is inseparable from the strangeness, because the interference pattern proves that each individual electron, each one a single indivisible particle, somehow traveled through both paths at the same time and interfered with itself. There was nothing else there. The electron was alone. And yet it behaved as if it had taken both routes simultaneously. Now the obvious question is, which slit did the electron actually go through? So physicists put a detector at one of the slits to find out. And the moment they did that, the interference pattern vanished. The electrons started behaving like normal particles, going through one slit or the other, never both. The act of detecting which path the electron took destroyed the very behavior they were trying to observe. Think about that for a second. When nobody is watching, the electron goes through both slits and creates a wave pattern. When someone watches, it goes through only one slit and behaves like a particle. The electron seems to know whether it's being observed. That result has been replicated thousands of times with increasing sophistication. It works with electrons, with photons, with neutrons, with atoms, with molecules. In 1999, Marcus Arndt and Anton Zeilinger's group in Vienna demonstrated interference with Buckminster fullerene molecules, little soccer ball structures made of 60 carbon atoms. By 2011, they'd pushed it to molecules of 430 atoms. By 2019, the record was molecules of roughly 2,000 atoms, with a mass exceeding 25,000 Daltons. These are not tiny quantum particles anymore. These are objects with tens of thousands of subatomic particles, and they still exhibit wave behavior. They still go through both paths at once, and they still stop doing that the moment you try to observe which path they took. The Vienna experiment from January 2025 pushed this even further. 7,000 atoms, 170,000 Daltons, the mass of a small virus. And it still worked. The interference pattern was still there, and it would still vanish the moment you tried to determine the particle's path. So the boundary between quantum weirdness and normal classical behavior keeps getting pushed further and further into the macroscopic world. Nobody has found the point where quantum mechanics stops working. Nobody has found the size at which objects stop being able to exist in two places at once. The only thing that reliably collapses the superposition is observation, measurement, the act of looking. But what does looking actually mean? This is where it gets uncomfortable, because in 1978, John Archibald Wheeler proposed a thought experiment that made the observer effect even stranger. Wheeler was one of the titans of 20th century physics. He worked on the Manhattan Project. He mentored Richard Feynman. He coined the terms black hole and wormhole. And in '78, at a symposium honoring Feynman, he proposed something called the delayed choice experiment. The idea is fiendishly simple. You set up the double-slit experiment with a twist. Instead of deciding before the experiment whether to detect which path the particle takes, you wait until after the particle has already entered the apparatus and is, presumably, already in flight. Only then do you choose whether to measure which path it took or whether to look for interference. Wheeler's question was, does the choice you make after the particle has already entered change what the particle did when it entered? The answer, confirmed experimentally, is yes. In February of 2007, Vincent Jacques, Alain Aspect, and their colleagues at the École Normale Supérieure performed the definitive version of Wheeler's experiment. They used single photons, a 48-meter interferometer, and a quantum random number generator that switched the measurement configuration millions of times per second. The switching happened so fast, and the distances were arranged so carefully that the photon could not possibly know which measurement it would face when it entered the apparatus. Relativity guaranteed that no signal could travel fast enough to warn it. The results were unambiguous. When the experimenters chose to look for interference, they found interference with 94% visibility, near perfect wave behavior. When they chose to detect which path, they found particle behavior. And it did not matter one bit that the choice was made after the photon had already entered the interferometer. The results were identical in normal mode and delayed choice mode. Wheeler's conclusion, stated in his characteristically vivid way, no elementary quantum phenomenon is a phenomenon until it is a recorded phenomenon. Think about what that implies. The photon enters the apparatus. It has to decide whether to behave as a wave and go through both paths, or behave as a particle and go through one path. But the experimenter hasn't decided yet which measurement to make. The experimenter decides later, after the photon is already in flight. And somehow, the measurement choice made later determines what the photon did earlier. This is not time travel. Nothing is traveling backward through time. But Wheeler's experiment demonstrates something that might be equally strange. The photon does not have a definite history. It does not go through one slit or both slits. It doesn't do anything definite until a measurement is made. The past, in some sense, is not fixed until the present observes it. Wheeler took this thought experiment to its most extreme conclusion. He imagined a cosmic version. Light from a distant quasar, billions of light years away, passes a massive galaxy that acts as a gravitational lens. The gravity of the galaxy bends the light, sending it along two different paths around the galaxy, just like two slits in a laboratory. The light has been traveling for billions of years along both paths simultaneously. Now, here on Earth, an astronomer sets up a telescope. If the astronomer uses one kind of detector, the photons show particle behavior. They came along one path or the other. If the astronomer uses a different detector, the photons show wave behavior. They came along both paths and interfere with each other. And the astronomer's choice, made today, in this moment, determines what the photon did billions of years ago. Not metaphorically, literally. The photon's history, stretching across billions of light years and billions of years of travel time, is not determined until the astronomer makes a measurement. Wheeler was very precise about this. We have no right to say what the photon is doing during its billion-year travel from the quasar to our telescope, he wrote. We are dealing with an elementary act of creation. It is wrong to say that the past already exists. The past exists only insofar as it is recorded in the present. This is either the most radical claim in the history of physics or a profound misunderstanding of quantum mechanics. The physics community, characteristically, decided to simply not talk about it. But the experiments keep confirming Wheeler's predictions every single time. In 2015, Andrew Manning and colleagues at the Australian National University repeated the experiment with massive atoms instead of photons, getting the same result. In 2017, Francesco Vedovato's team bounced photons off satellites thousands of kilometers away and made the measurement choice while the photons were in transit across that enormous distance. The result held. The scale doesn't matter. The distance doesn't matter. The timing doesn't matter. The observation always determines the outcome. And this brings us back to the question that physics has spent decades avoiding. If observation determines outcomes, then what counts as an observation? Is it the detector? The computer that records the detector's output? The physicist who reads the computer screen? Is it consciousness? Is it something else entirely? The standard answer from most physics textbooks is something like decoherence. When a quantum system interacts with a large, complex environment, the delicate quantum superposition gets scrambled. Information about the system leaks into the environment. and for all practical purposes, the superposition is destroyed. The system behaves classically. Decoherence is real, well understood, and measurable. A dust grain 1 micron across at room temperature decoheres in about 10 to the negative 36 seconds. A trillionth of a trillionth of a trillionth of a second. The environment observes it almost instantly. But here's the thing about decoherence that textbooks tend to gloss over. Decoherence explains why we don't see quantum behavior in everyday objects. It explains the practical emergence of classical behavior. What it does not explain is why any particular measurement gets any particular result. Decoherence turns a superposition of a live cat and dead cat into what looks like a classical mixture of a live cat or dead cat. But it doesn't tell you which one you get. It doesn't explain why you open the box and find the cat alive rather than dead. The specific outcome, the definite result, the thing that actually happens when you look, that remains unexplained. And this is not a minor technical detail. It is the central unsolved problem in the foundations of quantum mechanics. Decoherence is like explaining that a coin always lands on one side after you flip it because of air resistance and gravity. That's true, that's useful. But it doesn't tell you why this particular flip came up heads. Something selects the outcome, and after 100 years, nobody can tell you what that something is. And speaking of the cat, there is a popular misconception about Schrödinger's cat that is so widespread, it has essentially become the dominant understanding of the thought experiment. And it is almost exactly backwards. Most people think Schrödinger was proposing that cats can be alive and dead at the same time. That's how it's taught in pop science, how it appears in t-shirts and cartoons, how it's referenced in movies and TV shows. But Schrödinger was doing the opposite. He was attacking the Copenhagen interpretation. He was saying, look how absurd this theory is. If you take the standard formalism seriously, you end up with a cat that's both alive and dead. Obviously, that's ridiculous. Therefore, something is wrong with the standard formalism. Schrödinger invented his famous cat specifically to embarrass the Copenhagen interpretation, not to illustrate it. And the fact that his attack has been repurposed as an explanation tells you something about how thoroughly the physics community has avoided engaging with what the thought experiment actually means. The cat is supposed to make you uncomfortable. It's supposed to make you say, something has to resolve this superposition. Something has to determine whether the cat is alive or dead. And that something is the thing nobody wants to talk about, which is why, despite the discomfort it causes, some very serious physicists kept circling back to the most obvious and most troubling possibility, that the something might be consciousness. The idea that consciousness might play a fundamental role in quantum mechanics didn't come from mystics or New Age gurus. It came from one of the greatest mathematical minds of the 20th century. In 1932, John von Neumann published his Mathematical Foundations of Quantum Mechanics, a book so rigorous and so influential that it defined how physicists thought about quantum theory for decades. And buried in that formalism was a problem that von Neumann was honest enough to state clearly. Von Neumann identified two fundamentally different processes in quantum mechanics. Process 2 is the smooth, continuous, perfectly predictable evolution described by the Schrödinger equation. This is what happens to a quantum system when nobody is measuring it. The wave function evolves, superpositions form, everything is deterministic and mathematically elegant. Process 1 is the sudden, discontinuous, probabilistic collapse that occurs when a measurement is made. The superposition vanishes. A single definite result appears. Process 1 is random. It cannot be predicted. It follows the Bohm rule, which gives you the probabilities, but nothing in the math tells you which outcome actually occurs. The problem von Neumann wrestled with is called the von Neumann chain, and it's easier to understand than it sounds. Imagine you have a single electron in a superposition of spin up and spin down. You measure it with a detector. The detector clicks. You've got your answer. But wait, the detector is made of atoms. Those atoms obey quantum mechanics. When the electron interacts with the detector, quantum mechanics says the detector itself enters a superposition, not spin up and spin down anymore, but detector that registered up and detector that registered down. The superposition hasn't been destroyed. It has spread. Now the detector sends a signal to a computer. The computer is also made of atoms. The computer enters a superposition of displaying up and displaying down. The computer displays the result on a screen. The screen enters a superposition. The screen sends photons to your eye. Your retina absorbs the photons. The signal travels down your optic nerve to your brain. At every step, you can push the boundary between observed system and observer deeper and deeper. Von Neumann showed mathematically that no matter where you draw the line, the physics works out the same. You can treat the collapse as happening at the detector, at the computer, at the screen, at the retina, at the optic nerve, at the brain. The predictions are identical, but the collapse has to happen somewhere. Something has to break the chain. Something has to select a definite outcome from the superposition of possibilities. And von Neumann, in his precise and careful way, noted that the chain terminates at one point that is fundamentally different from all the others. His exact words, "Experience only makes statements of this type. An observer has made a certain subjective observation, and never any like this. A physical quantity has a certain value." Von Neumann didn't say consciousness causes collapse. He was too careful for that. But he left the door wide open. And in 1961, a Nobel laureate walked right through it. Eugene Wigner won the Nobel Prize in Physics in 1963 for his work on symmetry principles in nuclear physics. Born in Budapest in 1902, childhood friends with von Neumann himself, Wigner was nobody's idea of a crank. He was one of the most respected physicists of his generation, and in his 1961 paper, Remarks on the Mind-Body Question, he took von Neumann's logic to its radical endpoint. Wigner's argument was deceptively straightforward. Suppose a friend of mine performs a quantum measurement inside a sealed laboratory. From my perspective, outside the lab, quantum mechanics says the entire lab, including my friend, is in a superposition until I open the door and look. My friend has measured the particle and gotten a definite result. He knows the answer. But from my perspective, he's in a superposition of friend who got result A and friend who got result B. Now, Wigner said, this is fine if my friend is replaced by a machine. A machine in superposition doesn't bother anyone. But my friend is a conscious being. he experienced a definite result. He was not in suspended animation, waiting for me to open the door. Something about his consciousness, his subjective experience, collapsed the superposition before I ever looked. Wigner's conclusion stated plainly, it was not possible to formulate the laws of quantum mechanics in a fully consistent way without reference to the consciousness. And more dramatically, the very study of the external world led to the conclusion that the content of the consciousness is an ultimate reality. He went even further. Solipsism may be logically consistent with present quantum mechanics, Wigner wrote. Monism in the sense of materialism is not. Read that again. A Nobel Prize winning physicist, using the standard formalism of quantum mechanics, concluded that pure materialism is logically inconsistent with the theory. Consciousness, in his analysis, was not an emergent property of matter. It was the other way around. Matter was an emergent property of consciousness. The physics community reacted about the way you'd expect. Most ignored it. Some dismissed it. A few engaged with it seriously. But Wigner had done something that couldn't be undone. He'd shown that a perfectly legitimate reading of the standard quantum formalism leads directly to a role for consciousness. You can disagree with his conclusion. You can find ways around it. But you cannot pretend the argument doesn't exist, because it flows straight out of von Neumann's mathematics, which nobody disputes. What happened to Wigner himself is instructive. In the late 1970s and into the 80s, he began walking back his own position. The retreat was gradual and apparently painful. In a 1982 lecture, Wigner described his earlier views as tending towards solipsism, a conclusion he found philosophically repugnant. Part of his retreat was genuine intellectual evolution. A German physicist named H. Dieter Zeh had published a landmark paper in 1970 showing that quantum systems naturally become entangled with their environments, a process called decoherence, which explains why quantum superpositions become invisible at macroscopic scales without needing to invoke consciousness. Wigner found Zeh's work persuasive, or at least persuasive enough to provide cover for a retreat he may have wanted for other reasons. But part of the retreat was clearly social. Wigner was a Nobel laureate, one of the most respected physicists alive, and he had published a paper arguing that consciousness is an ultimate reality, more fundamental than matter. The professional embarrassment of this position, in a discipline that prided itself on hard-nosed materialism, weighed on him. Colleagues he respected made their discomfort clear, and Wigner, who cared deeply about his standing in the physics community, gradually softened his language until the original radical claim was barely recognizable. The irony is that Zeh's decoherence, which Wigner used to justify his retreat, doesn't actually solve the problem Wigner raised. Decoherence explains why we don't see cats in superposition. It does not explain why we see a particular cat, alive or dead. The measurement problem persists with or without decoherence. And Wigner's original question, what role consciousness plays, remains open. He retreated from an argument that still hasn't been answered. What happened next is even more revealing. Rather than confronting Wigner's argument head-on, the physics community developed an informal policy. Don't talk about it. Don't engage with it. Don't ask what the observer is. Just use the equations. They even had a phrase for this approach, usually attributed to Richard Feynman, but actually coined by a Cornell physicist named N. David Mermin in a 1989 article for Physics Today. The phrase was, "shut up and calculate," and Mermin meant it as satire. He was mocking the attitude, not endorsing it. As he wrote in a 2004 follow-up, nobody could ever have had the slightest reason to direct the best human calculator that ever was to shut up and calculate. But the phrase stuck, and for decades, it described exactly how most physicists dealt with the foundational questions. They shut up, they calculated, and they pretended the questions weren't there. Meanwhile, a handful of physicists kept pushing. Henry Stapp, a mathematical physicist at Lawrence Berkeley National Laboratory, who studied under Nobel laureates Segre and Chamberlain, spent decades building on von Neumann's framework. Stapp's argument is more sophisticated than the Wigner's and harder to dismiss. He identified 3 processes, not 2. Process 2 is the standard Schrödinger evolution. Process 3 is nature's probabilistic response when a measurement occurs, following the Bohm rule. But process 1, the choice of what question to ask nature, what measurement to perform, that, Stapp argued, is not determined by any known physical law. It is a free choice made by a conscious agent. Stapp then connected this to the quantum Zeno effect, the well-established phenomenon where rapidly repeated measurements can freeze a quantum system in a particular state. If a conscious agent can choose what to measure, and if rapid repeated measurement can hold a quantum state in place, then consciousness might be able to influence physical outcomes, not through telekinesis or mystical energy, but through the standard quantum formalism. His conclusion was provocative. Orthodox quantum mechanics considers these events to be instigated by choices made by conscious agents, Stapp wrote. Thus, orthodox von Neumann contemporary physics posits an interactive dualism similar to that of Descartes. Now, most physicists reject Stapp's argument. They find it unnecessary, philosophically loaded, or simply uncomfortable. But notice what they are not saying. They are not saying his physics is wrong. They are not saying he misapplied the formalism. They are saying they don't like the conclusion. And that's a very different thing. Roger Penrose, who won the Nobel Prize in Physics in 2020 for his work on black hole singularities, came at the consciousness question from a completely different angle. In his 1989 book, The Emperor's New Mind, Penrose argued that human consciousness is fundamentally non-algorithmic. His argument rested on Gödel's incompleteness theorems, one of the deepest results in all of mathematics. Gödel showed in 1931 that any consistent formal system powerful enough to express arithmetic contains true statements that the system itself cannot prove. A human mathematician can see that these statements are true, can understand why they're true, but no algorithm running inside the system can derive them. Penrose argued that this means human mathematical understanding cannot be the output of any computation. Something in the brain is doing something that no computer can do, no matter how fast or sophisticated. If consciousness is non-computable, Penrose argued, it can't be explained by classical physics or standard computation. Something else is going on, something that requires new physics. And Penrose thought he knew where to find it, in quantum mechanics. Working with Stuart Hameroff, an anesthesiologist at the University of Arizona, who had spent years studying the internal structures of cells, Penrose developed a specific proposal that would become one of the most controversial ideas in both physics and neuroscience. The target was microtubules. These are tiny cylindrical protein structures, about 25 nanometers in diameter, that form the structural skeleton inside every cell in your body, including neurons. They're made of a protein called tubulin, which exists in two slightly different configurations, alpha and beta. A single microtubule contains about 13 columns of tubulin proteins spiraling along its length. Hameroff had long believed that microtubules were more than just structural scaffolding. He thought they processed information, and he thought they might do so quantum mechanically. Penrose and Hameroff proposed that quantum superpositions form among tubulin states in microtubules, that these superpositions are orchestrated by biological processes, and that they undergo what Penrose calls objective reduction when they reach a critical threshold related to gravitational self-energy. This threshold is about a Planck mass, which is roughly the mass of a grain of sand. Each such reduction event constitutes a moment of conscious experience. The theory is called orchestrated objective reduction, or ORC-OR. And if it's right, it means that consciousness is a quantum gravitational phenomenon, that the brain is not a classical computer, but a quantum one, and that the moments of consciousness you experience are literally the collapse of quantum superpositions in the protein structures of your neurons. For years, ORC-OR was treated as somewhere between bold and ridiculous. Max Tegmark published a devastating critique in 2000, calculating that decoherence would destroy quantum effects in the brain in somewhere between 10 to the negative 13 and 10 to the negative 20 seconds. That's 100,000 billionth of a second at best. Neural processes, the firings and signaling events that constitute brain activity, happen on timescales of milliseconds, roughly 10 to the negative 3 seconds. The gap between the decoherence time and the neural time is 10 billion orders of magnitude. The brain is warm, wet, and noisy. It's possibly the worst environment in the known universe for maintaining quantum coherence. Tegmark's conclusion was definitive. The degrees of freedom of the human brain that relate to cognitive processes should be thought of as a classical rather than quantum system. Most physicists considered that the end of the story. ORC-OR was a beautiful idea that nature simply didn't support. But recent experiments have complicated that verdict. In 2023, a team at Princeton led by Kalra found that laser-induced excitations propagated through microtubules much further and persisted much longer than anyone expected, and critically, that anesthetics dampened this propagation. Think about that for a second. Anesthetics are the drugs that eliminate consciousness. If they also dampen quantum effects in microtubules, that's exactly what you'd expect if microtubules are involved in consciousness at the quantum level. It's not proof, but it's exactly the kind of coincidence that makes physicists sit up and pay attention. In 2022, Kerskens and Perez used unconventional MRI protocols at Trinity College Dublin and claimed to detect entangled brain states correlated with consciousness and working memory. The methodology is contested. The results are preliminary. But if confirmed, they would represent the first direct evidence of quantum effects playing a functional role in human cognition. In 2024, Babcock and colleagues published theoretical evidence for super radiant excitonic states in microtubules at room temperature. Superradiance is a quantum effect where many particles emit light collectively in a way that is qualitatively different from classical emission. If microtubules support superradiance at body temperature, it would undermine the assumption that biological systems are too warm for quantum effects. And in 2025, a paper by Wiest in Neuroscience of Consciousness argued that the quantum microtubule model is experimentally supported and solves the binding and epiphenomenalism problems. None of this proves OR is right. The evidence is preliminary, contested, and far from conclusive. But it makes the theory much harder to dismiss than it was a decade ago. And it's worth noting that David Chalmers, the philosopher who coined the hard problem of consciousness in 1994, has been remarkably open to quantum approaches. In a 2022 paper with Kelvin McQueen published by Oxford University Press, Chalmers explored consciousness collapse theories and concluded that the upshot is not that consciousness collapse interpretations are clearly correct, but that there is a research program here worth exploring. Chalmers has also been sharp in his criticism of OR specifically. Why should quantum processes in microtubules give rise to consciousness, he asked, any more than computational processes should? It's a fair question, and it points to the deeper puzzle. Even if quantum mechanics is involved in consciousness, we still don't know why any physical process, quantum or classical, gives rise to subjective experience. The hard problem remains hard, but the fact that quantum mechanics might be part of the answer rather than an irrelevant sideshow is itself a remarkable development. A research program worth exploring. That might be the most diplomatically devastating sentence in the philosophy of physics. Because what Chalmers is really saying is that a century after quantum mechanics was formulated, the possibility that consciousness plays a fundamental role has not been ruled out. It has not been refuted. It has not been explained away. It has mostly been ignored. And ignoring a question is not the same as answering it. When you poll physicists directly, the results are striking. In 2011, at a Quantum Foundations conference, Max Schlosshauer, Johannes Koffler, and Anton Zeilinger surveyed 33 leading experts. Only 6%, 2 people out of 33, believed the observer plays a distinguished physical role through consciousness. That sounds like the question is settled, but 36% had no preferred interpretation at all, and the remaining responses were scattered across half a dozen competing frameworks. The question isn't settled, it's just unfashionable. But if consciousness isn't the answer, then something else has to be. Because the measurement problem doesn't go away just because you stop talking about it. Something selects the outcome when a quantum measurement is made. Something collapses the superposition. Something turns the wave into a particle. And if that something isn't consciousness, then the alternatives might be even stranger, because the next logical step, the step that several of the 20th century's most brilliant physicists actually took, was to suggest that reality itself doesn't exist until it is observed. John Archibald Wheeler spent the first half of his career being one of the most respected conventional physicists alive. Manhattan Project, nuclear physics, general relativity. He mentored Feynman. He worked closely with Niels Bohr. He coined terms that became fundamental to how we think about the universe: black hole, wormhole, quantum foam. If there was an establishment in American physics, Wheeler was at its center. But beneath the professional accomplishments was a personal wound that shaped his later thinking in ways most people don't know about. Wheeler's younger brother Joe was killed in the Italian campaign in World War II. John Wheeler carried a specific guilt about this for the rest of his life. Not just the guilt of survival, but a gnawing question about timing. Wheeler had worked on the Manhattan Project. He had helped build the bomb, and the bomb ended the war in the Pacific, but it came too late to save his brother in Europe. Wheeler spent years asking himself, if the bomb had been ready sooner, could the war in Europe have ended differently? Could Joe have lived? This question about timing, about whether the past could have been different, about whether earlier actions could have changed later outcomes, permeated Wheeler's physics. It's no accident that his most famous thought experiment, the delayed choice experiment, is fundamentally about whether the present can reach back and influence the past. Wheeler never made the personal connection explicit in his published work, but colleagues who knew him well understood that the delayed choice experiment was not just physics. It was Wheeler working through the deepest question of his life: whether timing matters, whether the past is fixed, whether things could have been otherwise. And then, starting in the late 1970s, Wheeler's thinking took a turn that alarmed even his admirers. He began saying things like, no phenomenon is a real phenomenon until it is an observed phenomenon. He declared that the old term observer was obsolete and should be replaced by participant, because quantum mechanics had destroyed the notion of passive observation. Participant is the incontrovertible new concept given by quantum mechanics, Wheeler wrote. It strikes down the observer of classical theory, the man who stands safely behind the thick glass wall and watches what goes on without taking part. It can't be done, quantum mechanics says. Wheeler wasn't talking about consciousness. He was talking about something more radical. He was proposing that the universe itself has no definite properties until measurements create them. Not that the properties are hidden and we just can't see them. Not that the properties exist and we just don't know which ones they are. But that the properties genuinely do not exist until an act of measurement brings them into being. He had an analogy he loved to use, the surprise version of 20 questions. In the normal game, you leave the room while the other players agree on a word. You come back and ask yes or no questions. The word exists in the room, and your questions gradually reveal it. But in Wheeler's version, the players don't agree on a word. Instead, each player, when asked a question, thinks of something consistent with all previous answers and responds accordingly. The word is created through the process of questioning. It doesn't exist beforehand. As Wheeler put it, the word wasn't in the room when I came in, even though I thought it was. That's what Wheeler believed quantum mechanics was telling us about reality. The electron doesn't have a definite position before you measure it. It genuinely has no position. Your measurement doesn't reveal a pre-existing fact. It creates the fact. And Wheeler extended this all the way to cosmology. He proposed a cyclic relationship. Physics gives rise to observer participancy. Observer participancy gives rise to information, and information gives rise to physics. He He believed that we are, in his words, participators in bringing into being not only the near and here, but the far away and long ago. Coming from almost anyone else, this would have been dismissed as philosophy at best and mysticism at worst. Coming from Wheeler, it couldn't be ignored. This was the man who had worked with Bohr and mentored Feynman. He understood quantum mechanics as deeply as anyone alive, and he was saying that reality is not something we observe. It is something we create through the act of observation. In the spring of 1989, Wheeler crystallized his thinking into a three-word phrase that would become one of the most quoted ideas in modern physics. It from bit. His full formulation, it from bit. Otherwise put, every it, every particle, every field of force, even the space-time continuum itself, derives its function, its meaning, its very existence entirely, even if in some contexts indirectly, from the apparatus elicited answers to yes or no questions, binary choices, bits. Information, Wheeler was saying, is more fundamental than matter. Things exist because they are measured. Measurement produces information, and information is the foundation of physical reality. Wheeler died in 2008 at the age of 96. He did not live to see his ideas vindicated, but he would have recognized what came next. In 1996, an Italian physicist named Carlo Rovelli published a paper in the International Journal of Theoretical Physics that proposed something called relational quantum mechanics. Rovelli, born in Verona in 1956, was trained as a physicist but thought like a philosopher. He'd been active in Italian student protests before turning to physics. He co-developed loop quantum gravity. His popular books, 7 Brief Lessons on Physics, The Order of Time, and especially Helgoland in 2021, made him arguably the most widely read physicist-philosopher of his generation. Rovelli's central claim was breathtaking in its simplicity. Quantum mechanics, he argued, is telling us that properties do not belong to objects. Properties only exist relative to interactions. A particle doesn't have a definite spin. It has a spin relative to the device that measures it. And a different device, interacting differently, might find a different spin. Not because the measurement is imperfect, not because there's hidden information, but because spin, position, momentum, all properties are not features of objects. They are features of relationships between objects. Consider a bowling ball sitting on a table. It seems obvious that the ball has a weight, a color, a size. These properties seem to belong to the ball intrinsically, regardless of whether anyone is measuring them. Rovelli says quantum mechanics is telling us that this intuition is wrong. The ball's weight only exists relative to the scale that measures it. Its color only exists relative to the light that bounces off it and the eye that detects that light. Its size only exists relative to the ruler laid alongside it. Strip away all the interactions, all the measurements, all the relationships, and there is nothing left. Not because the ball disappears, but because the ball was never a self-contained thing with intrinsic properties. It was always a node in a web of relationships. And quantum mechanics, Rovelli believes, is the first theory in physics to make this explicit. I suggest that the common unease with taking quantum mechanics as a fundamental description of nature, Rovelli wrote in his original abstract, could derive from the use of an incorrect notion, the notion of observer-independent state of a system. In his book, Helgoland, he put it more vividly. Is it possible that a fact might be real with respect to you and not real with respect to me? Quantum theory, I believe, is the discovery that the answer is yes. And in an October 2025 interview with Quantum magazine, Ravelli stated it as plainly as it can be stated. There is no objective reality, only perspectives. This is not the same as Wheeler's participatory universe, but it rhymes with it. Wheeler said reality is created through measurement. Ravelli says reality is always relative to an observer. Both are saying that the idea of an objective, observer-independent universe, the universe that exists out there, whether anyone is looking at it or not, is an assumption that quantum mechanics forces us to abandon. Running parallel to Ravelli's work is a framework called Cubism, developed by Christopher Fuchs, N. David Mermin, the man who coined Shut Up and Calculate, and Rüdiger Schack. Cubism stands for quantum Bayesianism, and its central claim is that quantum states are not descriptions of reality. They are descriptions of an observer's beliefs about future measurement outcomes. Wave function collapse isn't a physical event. It's an observer updating their beliefs in light of new information, exactly the way a Bayesian updates their probability estimates. Now, this might sound like Cubism is denying that reality exists. It's not. And understanding why it's not is crucial to understanding why these ideas matter. Fuchs arrived at Cubism through a long engagement with the deepest problems in quantum mechanics. He worked at Bell Labs at the University of Cambridge and at the Perimeter Institute before landing at the University of Massachusetts, Boston. Along the way, he built a massive archive of correspondence about quantum foundations, literally thousands of emails with other physicists wrestling with what quantum mechanics means. His journey is instructive because it mirrors the journey of the field itself, from hoping that some clever reinterpretation could make the weirdness go away, to gradually accepting that the weirdness is the point. Fuchs coined the term participatory realism to describe what Cubism is actually saying. Reality exists, but reality is not something you can describe from the outside as a spectator. Every description of reality is a description from somewhere by someone. There is no view from nowhere. There is no God's eye perspective that captures everything. Each observer's experience is genuine. Each observer's quantum state reflects their own unique relationship with the world. And there is no master quantum state that encompasses all observers and all perspectives. Quantum mechanics is a law of thought, Fuchs has said. Not a law about things out there, but a law about the relationship between observers and the world they participate in. The most common objection to Cubism is that it's just solipsism dressed up in mathematical language. Fuchs has spent years fighting this characterization. That's not less reality, that's more, he insists. The world doesn't disappear when you adopt Cubism. It becomes richer. Instead of one flat objective reality that we all passively observe, you get a universe teeming with perspectives, each one genuine, each one irreducible, each one a real relationship between an agent and the world around them. He has described Cubism as carrying Wheeler's participatory insights to their logically furthest extent. Mermin, who joined Fuchs in developing Cubism in his later years, found it liberating after decades of frustration with the standard approach. The man who coined "shut up and calculate" as satire spent the last phase of his career arguing that the phrase described the worst possible approach to quantum mechanics. His conversion from critic to advocate of cubism is one of the quiet ironies of quantum foundations. 3 different frameworks: Wheeler's participatory universe, Ravelli's relational quantum mechanics, and Fuchs's cubism. They disagree on details. Wheeler focused on information, Ravelli focused on relations, Fuchs focused on personal experience, but they all converge on the same fundamental claim. The observer is not a passive recorder of pre-existing facts. The observer is a participant in the creation of reality. And the concept of a universe that exists independently of all observation may not be coherent. And then, in late 2025, a result from quantum gravity made this convergence look less like philosophy and more like physics. The story begins in 2019, when Juan Maldacena and colleagues were studying quantum gravity in closed universes that are finite and have no boundary. They found something deeply paradoxical. A closed universe, described quantum mechanically, admits only a single possible quantum state. One state. That means zero information content, no complexity, no structure, nothing. A universe with no observers doesn't just lack observers, it lacks everything. This sat as a troubling puzzle for several years until, in early 2025, Ying Zhao at MIT, along with Daniel Harlow and Mikhailo Usatiuk, proposed a resolution. Their insight was that placing an observer inside the closed universe changes everything. The observer introduces a new kind of boundary, the boundary of the observer themselves, their own body, their own measurement apparatus. And when you include that boundary in the calculation, all the complexity of the world returns. The universe goes from one state to an astronomically vast number of states. Structure, information, physics itself, all come flooding back. Think about what that means. Without an observer, the mathematics says the universe has no information. With an observer, it has everything. The observer isn't just measuring reality. The observer is, in some deep mathematical sense, what makes reality possible. The Quantum magazine article covering this result noted, with evident astonishment, if the idea holds up, this view from nowhere seems less and less viable. Perhaps views from somewhere are all that we can ever have. Wheeler would have recognized this immediately. The universe gives birth to consciousness, he once said, and consciousness gives meaning to the universe. The 2025 quantum gravity result doesn't prove Wheeler was right, but it suggests that the mathematical structure of reality may be fundamentally entangled with the presence of observers. Not consciousness specifically, not subjective experience necessarily, but observation in the broadest sense. The act of one part of the universe gathering information about another part. And that would mean the observer effect isn't just a quirk of laboratory quantum mechanics. It would mean observation is built into the structure of reality at the deepest level. The universe doesn't just allow observers, it may require them. But if the observer plays this fundamental a role, a disturbing question follows. If your observations help create reality, are your observations free? Do you actually choose what to measure? Or is that choice itself determined by the prior state of the universe? Because if your choices aren't free, the entire framework changes. And there's a theorem that says the answer to this question has consequences far more unsettling than anyone expected. In 2006, 2 mathematicians at Princeton University published a theorem so uncomfortable that most physicists pretend it doesn't exist. Their names were John Conway and Simon Kochen. Conway was already famous. He'd invented the game of life, one of the most influential mathematical constructions of the 20th century, and he was widely regarded as one of the most creative mathematicians alive. Kochen was a distinguished logician. Together, they proved something they called the free will theorem. The theorem makes a very precise claim. It says that if experimenters have free will, meaning if they can freely choose what measurement to perform on a quantum particle, then the particle's response cannot have been determined by the entire prior history of the universe. The particle, in Conway and Kochen's language, must also have free will. Its behavior is not pre-programmed. It is not the inevitable consequence of everything that came before. It is, in some rigorous mathematical sense, spontaneous. The theorem rests on three axioms. Spin. Squared spin measurements of certain particles always yield specific values. Twin. Entangled particles produce correlated results. And min. The experimenter's choice of measurement direction is not determined by the particle's prior state. All three axioms are well-tested consequences of quantum mechanics and special relativity. There is nothing controversial about any of them individually. But when you put them together, the logical consequence is that either human experimenters don't have free will, or particles aren't deterministic. There is no middle ground. Conway was passionate about this result. "I just decided to throw that piece of paper on the floor," he said in an interview. "I don't believe that was determined at the start of the Big Bang, 14 billion years ago. I think it's ludicrous to imagine that the entire development of the universe, including, say, this interview, was predetermined." Now, there is exactly one way to escape the free will theorem and Bell's theorem and all the related results that show quantum mechanics violates classical expectations. That escape route is called superdeterminism. And the story of superdeterminism is one of the most contentious chapters in modern physics. The idea is this: in every Bell test experiment, in every test of quantum mechanics against classical expectations, there is an assumption. The assumption is that the experimenter can freely choose what to measure. They point their detector this way or that way, and the choice is independent of the particle's properties. Superdeterminism says this assumption is wrong. The experimenter's choice and the particle's properties are both determined by prior causes stretching all the way back to the Big Bang. The experimenter thinks they're choosing freely, but they're not. Their choice was fixed by the initial conditions of the universe, correlated with the particle's properties from the very beginning. If superdeterminism is true, Bell's theorem doesn't apply. The free will theorem doesn't apply. Quantum mechanics can be explained by hidden variables after all. Everything is deterministic. There is no randomness. There is no free will. The universe is a vast clockwork mechanism that was fully determined at the moment of the Big Bang, and every quantum measurement, every experimental choice, every thought you've ever had was inevitable from the start. The most prominent physicist who has seriously explored this idea is Gerard 't Hooft, who won the Nobel Prize in 1999 for his work on the electroweak force. 't Hooft developed something called the cellular automaton interpretation, published as a book by Springer in 2016, in which quantum mechanics emerges from a completely deterministic underlying system. and Hooft has a fascinating anecdote about discussing this with John Bell himself. "I raised the question," Hooft recalled. "Suppose that also Alice's and Bob's decisions have to be seen as not coming out of free will." Bell's response, "Well, you know, that I have to exclude. If it's possible, then what I said doesn't apply." Bell knew. He understood the loophole perfectly. He just thought it was too high a price to pay. And he wasn't alone. Sabine Hossenfelder, a theoretical physicist and popular science communicator, became the most vocal contemporary advocate for superdeterminism, co-authoring a paper with Tim Palmer in Frontiers in Physics in May of 2020, titled Rethinking Superdeterminism. Her core argument: the reason we can't predict the outcome of a quantum measurement is that we are missing information. In other words, hidden variables exist. We just can't access them because of the superdeterministic correlations. The backlash was fierce and immediate. Anton Zeilinger, who would go on to win the Nobel Prize in 2022 for his Bell test experiments, argued that if superdeterminism were true, it would make no sense at all to ask nature questions in an experiment, since then nature could determine what our questions are. Think about what Zeilinger is saying. If superdeterminism is true, science itself might be unreliable, because you can never be sure your experimental choices aren't being manipulated by the same deterministic process you're trying to study. Howard Wiseman and Eric Cavalcanti, both respected quantum foundations researchers, wrote that superdeterminism would be about as plausible and appealing as belief in ubiquitous alien mind control. Tim Maudlin, a philosopher of physics at New York University, offered a devastating analogy. Superdeterminism, he said, is like a tobacco company, arguing that the correlation between smoking and cancer doesn't prove causation, because some hidden variable, determined at the Big Bang, independently caused both the smoking and the cancer. It's logically possible, but it undermines the entire basis of experimental science. Bell's own words on the subject are worth hearing directly in a 1985 BBC radio interview, later published in a book called The Ghost in the Atom. Bell said, "There is a way to escape the inference of superluminal speeds and spooky action at a distance, but it involves absolute determinism in the universe, the complete absence of free will. Suppose the world is superdeterministic. The difficulty disappears. There is no need for a faster than light signal to tell particle A what measurement has been carried out on particle B, because the universe, including particle A, already knows what that measurement and its outcome will be." Bell acknowledged the escape route existed, and then, in his final major paper, written in 1990 and titled La Nouvelle Cuisine, he added this: "I do not expect to see a serious theory of this kind." But acknowledging the loophole wasn't enough for experimentalists. They wanted to close it, or at least push it to such an absurd extreme that accepting it would require believing in a conspiracy stretching across billions of years. In August of 2018, Anton Zeilinger's group, working with David Kaiser from MIT and Andrew Friedman, published one of the most extraordinary experiments in the history of physics. They called it the Cosmic Bell Test, and the story of how it came together is itself remarkable. David Kaiser is unusual in the physics world. He's both a working physicist and a historian of science. He'd spent years studying the cultural suppression of quantum foundations, documenting how Bohm and Bell and Everett were marginalized. And he understood, perhaps better than anyone, that the freedom of choice loophole wasn't just a technical concern. It was the last refuge of local realism. If you could close it, you'd push superdeterminism from implausible to effectively absurd. Kaiser's idea was elegant. Instead of using a random number generator or a human experimenter to choose measurement settings, use light from distant quasars. Quasars are supermassive black holes at the centers of ancient galaxies, blasting out light that has been traveling across the universe for billions of years. The color of each arriving photon, its precise wavelength, was determined by astrophysical processes that occurred billions of years before Earth existed. Use that wavelength to set the measurement angle, and any superdeterministic conspiracy would have to reach back to the epoch when the quasar light was emitted. Working at the Roque de los Muchachos Observatory on La Palma in the Canary Islands, the team performed a Bell test where the measurement settings were determined by the actual wavelength of photons from two distant quasars. One quasar's light was emitted 7.8 billion years ago. The other's was emitted 12.2 billion years ago. The experiment used a pair of 1-meter telescopes pointed at the quasars, with the arriving photons fed through filters and fast electronics that translated each photon's color into a measurement setting for the Bell test detectors below. Think about what that means. The measurement settings were determined by events that occurred billions of years before Earth existed, before the solar system formed, before most of the stars in the Milky Way had been born. The quasar that emitted the older light did so when the universe was only 1.5 billion years old, barely 11% of its current age, if superdeterminism is behind the quantum correlations. The conspiracy would have to stretch back to that epoch, to a time when the universe was a fraction of its present size, and it would have to somehow know that 12.2 billion years later, on a small island off the coast of Africa, a group of physicists would build a specific experiment and use these specific photons to set the measurement angles. The team collected data over 2 nights. They recorded more than 30,000 entangled photon pairs. The result? Bell's inequality was violated by 9.3 standard deviations. That's a p-value of less than 7.4 times 10 to the negative 21. To put that in perspective, the standard threshold for declaring a discovery in particle physics is 5 standard deviations. This was nearly twice that. The experiment excluded local realist mechanisms from 96% of the space-time volume of the observable universe's past light cone. The only remaining 4% corresponds to the earliest moments of the universe, the first fraction of a second after the Big Bang, before the quasar photons were emitted. Alan Guth at MIT, the physicist who developed the inflationary model of the universe, put it bluntly. If some conspiracy is happening to simulate quantum mechanics by a mechanism that is actually classical, that mechanism would have had to begin its operations, somehow knowing exactly when, where, and how this experiment was going to be done, at least 7.8 billion years ago. Kaiser reflected on the result with characteristic understatement. We've outsourced the choice to the cosmos, he said. And the cosmos confirmed quantum mechanics. And as if that weren't enough, there's the Big Bell test, which took a completely different approach to the freedom of choice problem. And in many ways, it's an even more beautiful experiment because it put humans at the center of the physics. On November 30th, 2016, something unprecedented happened in the history of science. More than 100,000 human volunteers from every inhabited continent sat at their computers and participated in a physics experiment. They didn't need to understand quantum mechanics. They didn't need a degree. They just needed to press buttons. The game was called the Big Bell Quest. Each volunteer was shown a simple interface and asked to generate sequences of zeros and ones as randomly as they could. Just press 0 or 1 as unpredictably as possible, over and over again. The game was deliberately designed to be fun, with graphics and scoring and competitive elements, because the organizers needed people to keep pressing buttons for hours. They needed the bits to keep flowing. And flow they did. Over the course of 12 hours, the 100,000 volunteers generated 97 million human-made random bits, 97 million tiny acts of free will, if free will exists, 97 million decisions about whether to press 0 or 1, each one made by a human brain in real time, each one unpredictable even to the person making it. Those bits were transmitted through the internet in real time to 12 different laboratories on 5 continents. In Vienna, the bits controlled the measurement settings for entangled photon experiments. In Munich, they set the angles for single trapped rubidium atoms. At the University of Science and Technology of China, they controlled atomic ensembles. At the National Institute of Standards and Technology in Boulder, they drove superconducting quantum interference devices. In Barcelona, in Buenos Aires, in Brisbane, in Concepcion, Chile, 12 labs, all running simultaneously, all controlled by the unpredictable choices of ordinary people sitting at home. At each laboratory, the arriving bits determined the measurement settings in Bell tests, and at every lab, using every type of quantum system, with settings determined by human choices rather than machines, the results were the same. Local realism was violated by more than 8 standard deviations across the combined dataset. Quantum mechanics won. Again, but this time with a twist that made the result philosophically different from anything that had come before. Morgan Mitchell, the experimental physicist at ICFO Barcelona, who organized the entire effort, made the point explicitly. Local realism is a question we can't fully answer with a machine. It seems we ourselves must be part of the experiment to keep the universe honest. Think about that sentence carefully. Mitchell is saying that the question of whether reality is locally realistic, the most fundamental question in physics, cannot be settled without human beings participating. Machines generate pseudo-random numbers using algorithms, and algorithms are deterministic. Even quantum random number generators produce their randomness through the very quantum effects being tested, which creates a logical circularity. But human choices, if they are genuinely free, break the circle. The experiment only works if the observers are free, and the observers, all 100,000 of them, chose freely, or at least they experienced choosing freely. And quantum mechanics passed the test. So where does all of this leave us? The cosmic bell test pushes any superdeterministic conspiracy to 7.8 billion years before the experiment. The Big Bell test uses human free choices as measurement settings, which means superdeterminism would have to control not just the physics of distant quasars, but the real-time decisions of 100,000 human beings simultaneously. You can still believe in superdeterminism. It's logically possible. It has not been ruled out, and it cannot be ruled out by any finite experiment, because you can always push the conspiracy further back. But the price keeps rising. To save determinism, to avoid the conclusion that the observer's free choices matter, you have to accept a universe where every experimental result, every quantum measurement, every human decision was fixed at the beginning of time, where your feeling of choosing what to have for breakfast this morning was an illusion caused by initial conditions set 14 billion years ago, where the entire history of the universe, including this sentence, was inevitable, and the alternative is that the observer effect is telling us something real about the role of observation in the universe. That measurement creates outcomes rather than revealing them, that the observer is not passive but participatory. That free will, or at least something functionally identical to it, is woven into the laws of physics at the most fundamental level: Conway and Cochin's theorem, Bell's experiments, the cosmic Bell test, the Big Bell test, the delayed choice experiments, the Wigner's Friend experiments, the 2025 quantum gravity results. They all point in the same direction. The observer is not an afterthought in the physics. The observer is central, and the fact that the physics community spent decades trying not to talk about this is itself part of the story, because the people who did try to talk about it paid a price that makes the silence understandable, even if it doesn't make it forgivable. David Bohm was, by any reasonable measure, one of the most gifted theoretical physicists of the 20th century. Born in Wilkes-Barre, Pennsylvania in 1917, the son of a Hungarian-born furniture store owner, Bohm showed early brilliance and earned his PhD at Berkeley under J. Robert Oppenheimer. He worked on the Manhattan Project during the war, though his security clearance was revoked before the work began, and he contributed through theoretical calculations at a distance. After the war, he took a position at Princeton, where he wrote a quantum mechanics textbook in 1951 that was so clear and so rigorous that Einstein himself told Bohm it was the best presentation of quantum mechanics he had ever seen. But Bohm was not content to simply present quantum mechanics. He wanted to understand it, and in 1952, he published a paper that proposed a complete alternative to the standard Copenhagen interpretation. In Bohm's version, particles have definite positions at all times. They are guided by a pilot wave, a real physical field described by the Schrödinger equation. There is no collapse. There is no measurement problem. There is no role for the observer. The theory reproduces every prediction of standard quantum mechanics while maintaining a completely deterministic, realistic picture of the world. The physics establishment's response was not scientific. It was personal, political, and ruthless. Part of the problem was timing. Bohm had been called before the House Un-American Activities Committee in 1949 because of his past associations with Communist Party members at Berkeley. He pleaded the Fifth Amendment and refused to testify against his colleagues. He was arrested and indicted for contempt of Congress, though he was later acquitted. But the damage was done. Princeton refused to renew his contract in June of 1951 and banned him from campus. Not suspended, banned. He could not enter the buildings where he had taught. He could not use the library. He could not meet with students. This was J. Robert Oppenheimer's Princeton, and Oppenheimer, the same man who had supervised Bohm's Ph.D., actively worked to suppress Bohm's 1952 paper on hidden variables. When other physicists asked Oppenheimer about it, his response was dismissive. The physics community took its cue from the top. Unable to find work in the United States, Bohm accepted a position at the University of Sao Paulo in Brazil. He left the country in October of 1951. 1 month after his arrival, the American consul in Sao Paulo confiscated his passport. Think about what that means. A brilliant physicist, driven out of his country by political persecution, arrives in a foreign land and then has his passport taken away by his own government. He was effectively imprisoned in Brazil. He could not travel to international conferences. He could not return home. He could not collaborate with colleagues abroad. When he applied for Brazilian citizenship, in order to get travel documents, the US State Department responded by formally revoking his American citizenship. It would not be restored until 1986, 35 years later. Bohm eventually found his way to Israel, then to England, settling at Birkbeck College in London in 1961. He continued working on foundations of quantum mechanics, on what he called the implicate order, on dialogue and philosophy. He became a close friend of the Indian philosopher Jiddu Krishnamurti and explored the relationship between physics and consciousness in ways that made his mainstream colleagues even more uncomfortable. He never received the recognition his physics deserved. His pilot wave theory, now usually called de Broglie-Bohm theory, was ignored by mainstream physics for decades. In the 2011 survey of Quantum Foundation's experts, 0% preferred it. By the 2025 Nature survey, it had climbed to 7%, a remarkable recovery for a theory that had been actively suppressed. When asked about his exile, Bohm responded with characteristic defiance. "It liberated me," he said. "I was able to think more easily and more freely." But his story was not unique. The physicist who proved that Bohm's questions were not only legitimate, but experimentally testable, paid a different kind of price. And his story is, if anything, even more tragic, because John Bell didn't live long enough to see his own predictions confirmed. Bell was born in 1928 in working-class Belfast, Northern Ireland. His family had no scientific connections. His mother sewed his academic gown from blackout curtains, left over from the war. He went to Queen's University Belfast, then to Birmingham, and in 1960, he joined CERN in Geneva. His official job was accelerator physics and particle physics. That was what paid the bills. Quantum foundations, the questions that consumed his intellectual life, were what he called his hobby, perhaps his obsession. He could only work on them in spare time, during evenings and weekends, or during sabbaticals. In 1964, during a year's sabbatical leave from CERN, Bell wrote the paper that would eventually reshape the foundations of physics. He proved that no local hidden variable theory could reproduce all the predictions of quantum mechanics. The proof was elegant, devastating, and published in a journal that almost nobody read, Physics Physique. Physica was a short-lived publication that folded a few years after Bell's paper appeared. In its first 6 years, the paper accumulated fewer than a dozen citations. Fewer than 12 people cited the most important result in quantum foundations in the second half of the 20th century. Bell's frustration with the culture of silence was deep and long-standing. He described what had happened in precise, bitter language. Making a virtue of necessity, he wrote, many came to hold not only that it is difficult to find a coherent picture, but that it is wrong to look for one, if not actually immoral, then certainly unprofessional. Unprofessional, that was the word. Asking what quantum mechanics means was unprofessional. Trying to understand the theory that describes the fundamental behavior of reality was a career risk. Bell watched as colleagues who should have been engaging with the deepest questions in physics instead looked away, either because they genuinely believed the questions were meaningless or because they were afraid of what would happen if they didn't. Bell died of a cerebral hemorrhage on October 1st, 1990, at the age of 62. His wife Mary was also a physicist at CERN. He died 25 years before the loophole-free Bell tests of 2015 would finally confirm his predictions beyond any reasonable doubt, and 32 years before the Nobel Committee would recognize the experimental work his theorem had inspired. There is a widely repeated story that Bell was being considered for a Nobel Prize at the time of his death. Whether or not that is true, the irony is inescapable. The man who proved that the foundations of quantum mechanics could be experimentally tested, the man who showed that the questions everyone was avoiding had real, measurable answers, died before the experiments were done and the prizes were given. And then there was Hugh Everett III, whose story is the darkest of all. Everett was a graduate student at Princeton in the early 1950s, working under Wheeler. In 1954, after what he later described as a slosh or two of sherry with his classmate Charles Misner and Aga Peterson, who was Niels Bohr's personal assistant, Everett conceived an idea that would become one of the most famous and most controversial proposals in the history of physics. His idea was simple and radical. What if the wave function never collapses? What if superpositions never end? What if, instead of one outcome being selected and the others vanishing, all outcomes happen and the universe splits into branches, one for each possible result? In one branch, the electron goes through the left slit. In another branch, it goes through the right slit. Both branches are equally real. Both continue to evolve according to the Schrödinger equation. The observer in each branch sees only one result, but the full quantum state, the universal wave function, contains all results simultaneously. This was Everett's many worlds interpretation, though he didn't call it that. He called it the relative state formulation. And in one stroke, it eliminated the measurement problem entirely. There is no collapse. There is no role for the observer. There is no mystery about what selects a particular outcome. Everything happens. You just happen to find yourself in one particular branch. The reception was catastrophic. Bohr, the towering figure of 20th century quantum mechanics, dismissed the idea when Everett visited Copenhagen for 6 weeks in 1959. Wheeler, Everett's own advisor, who had initially been enthusiastic, grew increasingly uncomfortable with the implications. He was not happy to have his own name associated with Everett's ideas, according to historical accounts. In 1980, Wheeler formally renounced the theory, saying it creates too great a load of metaphysical baggage. Everett was crushed. Discouraged by the scorn of other physicists, one account reads, Everett ended his physics career after completing his PhD. He himself put it more bluntly, I had washed my hands of the whole affair in 1956. He went to work at the Pentagon. He founded defense contracting companies. He made money, but he never returned to physics. By all accounts, he descended into heavy drinking, chain smoking, and obesity. He rarely spoke about quantum mechanics. He felt betrayed by the community that should have taken his ideas seriously, and most of all by Wheeler, the man who had mentored him, and then distanced himself when the intellectual establishment pushed back. Hugh Everett III died in bed on July 19, 1982, of a heart attack. He was 51 years old. His son Mark, who would later become the frontman of the rock band Eels, found the body. In an interview years later, Mark described the moment. Feeling the cold body, he said, I realized I had no memory of ever touching my dad before. In 1996, Everett's daughter Elizabeth took her own life. She reportedly said she wanted to join her father in a parallel universe. Wheeler, near the end of his own life, reflected on what had happened. He was disappointed, perhaps bitter, at the non-reaction to his theory. Wheeler said in a 2006 interview, How I wish that I had kept up the sessions with Everett. The questions that he brought up were important. Important. That might be the most painful word in the sentence. Wheeler spent decades knowing the questions were important, and decades not saying so loudly enough. By the time he admitted it publicly, Bohm had been dead for 14 years, Bell for 16, and Everett for 24. 3 physicists who asked what the observer effect means. One was exiled from his country. One died before his work was recognized. One was so discouraged that he abandoned physics entirely and drank himself to death at 51. And the questions they asked, the questions that cost them their careers and in some cases their lives, are the same questions that 100 years of quantum mechanics have still not answered. What connects these 3 stories is not just tragedy. It is a pattern. Each of them saw the same thing. Each of them recognized that the observer effect was pointing towards something profound about the nature of reality, and each of them was punished not for being wrong, but for being ahead of their time. Bohm's pilot wave theory reproduces every prediction of standard quantum mechanics. Bell's theorem is now the foundation of an entire field and the basis for a Nobel Prize. Everett's many worlds interpretation is the second most popular interpretation among working physicists today. They were right, and they suffered anyway. This should bother you. It bothers me. Not because the physics community is uniquely cruel, but because it shows how even the most rational and evidence-driven discipline on Earth can suppress inconvenient truths when the social incentives push hard enough in the other direction. Physicists are supposed to follow the evidence. They are supposed to question assumptions. They are supposed to be skeptical of received wisdom. These are the founding principles of science. And yet, on the most fundamental questions about the nature of their own theory, they spent decades doing exactly the opposite. The culture that destroyed Bohm and marginalized Bell and broke Everett didn't emerge from nowhere. It had a logic to it, even if that logic was ultimately self-defeating. To understand why physicists spent decades refusing to talk about what quantum mechanics means, you have to understand what happened to physics in the years after World War II. Before the war, the founders of quantum mechanics argued about interpretation constantly. Einstein and Bohr debated for decades. Schrödinger invented his cat specifically to show how absurd the Copenhagen interpretation was. De Broglie proposed pilot wave theory in 1927. These were the titans of physics, and they treated foundational questions as central to the discipline. The debates were heated, public, and considered essential. Then the bomb dropped. Literally. Physics had built the most destructive weapon in human history, and suddenly, the discipline had money, power, and social prestige it had never imagined. The US government poured funding into physics. Universities expanded their departments. National laboratories multiplied, and the funding came with an implicit expectation: produce results, build things, advance technology, win the Cold War. In this environment, philosophical questions about the meaning of quantum mechanics were worse than useless. They were a distraction. You could get a grant to build a laser. You could get a grant to design a transistor. You could get tenure by publishing calculations that matched experimental data. But you could not get funding. You could not get published in top journals. And you could not advance your career by asking what the wave function means. The incentive structure was clear. Calculate. Don't interpret. Produce results. Don't ask what the results mean. Von Neumann's 1932 proof that hidden variable theories were impossible provided intellectual cover for this attitude. If the alternatives had been mathematically ruled out, then asking about them was not just unproductive, but actively wrong-headed. The fact that von Neumann's proof contained a subtle error, an error that Bell would identify decades later, didn't matter. Nobody was checking. Nobody wanted to check. The proof served its social function. It gave physicists permission to stop worrying. David Bohm captured the resulting culture in a single devastating sentence. Everybody plays lip service to Bohr, but nobody knows what he says. People then get brainwashed into saying Bohr is right, but when the time comes to do their physics, they are doing something different. This was the world Bell was working in when he proved that the foundational questions had experimentally testable consequences, and this was why his paper gathered fewer than 12 citations in 6 years. The community wasn't interested. They had calculated their way to lasers and semiconductors and nuclear reactors, and the calculations worked without needing to understand what was underneath them. Why bother? But there was always a tension in this approach, because quantum mechanics is strange. It is deeply, fundamentally, inescapably strange, and no amount of calculating can make that strangeness go away. Every physicist who teaches the double-slit experiment feels it. Every graduate student who encounters the measurement problem for the first time feels it. The standard response, taught in classrooms around the world, is some version of "don't worry about it," or "that's just how quantum mechanics works," or "the math gives you the right answers, so use the math and stop asking questions." But the feeling never quite disappears. The surveys prove it. In 2011, Max Schlosshauer, Johannes Kofler, and Anton Zeilinger conducted the first serious polls of experts at a Quantum Foundations conference. They asked 33 leading physicists which interpretation of quantum mechanics they preferred. The results were all over the map. 42% chose some version of the Copenhagen interpretation, but there was no consensus on what Copenhagen actually means. 18% chose many worlds, 24% chose information-based or cubist approaches. And here's the number that matters most. Not a single respondent chose de Broglie-Bohm theory. 0%. The theory that Bohm was exiled for proposing. The theory that Einstein praised. The theory that is mathematically equivalent to standard quantum mechanics and makes all the same predictions was chosen by nobody. The suppression had worked that thoroughly. Sean Carroll, a theoretical physicist at Johns Hopkins, looked at the 2011 results and called them the most embarrassing graph in modern physics. His point was devastating. Quantum mechanics has been around since the 1920s at least, Carroll wrote, and yet we don't understand it. A larger survey in 2016 by Sivasundaram and Nielsen polled 149 physicists at 8 universities. Copenhagen led again at 39%. Many worlds dropped to 6%. But the most telling number was this. 36% said they had no preferred interpretation at all. More than a third of working physicists, people who use quantum mechanics every single day, had no opinion about what it means. And then came the 2025 Nature Survey, the largest ever conducted. Over 15,000 physicists were contacted. More than 1,100 responded. Copenhagen led at 36%. Many worlds was at 15%. Bohmian mechanics, after decades of suppression, had climbed to 7%. But the numbers that should trouble every physicist are these. Only 24% of respondents said they were confident their preferred interpretation was correct. 75% believed quantum mechanics would eventually be replaced by a more complete theory. And 85% agreed that interpretive work is valuable. Renato Renner, a leading quantum information theorist at ETH Zurich, looked at the 2025 results and identified the core problem. The implication, Renner said, is that many quantum researchers simply use quantum theory without engaging deeply with what it means, the shut up and calculate approach. A century after quantum mechanics was born, 3/4 of its practitioners think the theory is incomplete. Less than a quarter are confident in their own interpretation, and the overwhelming majority believe the foundational questions are worth asking. And yet, for decades, the professional culture made it dangerous to ask them. The surveys reveal a discipline at war with itself. Physicists know the questions matter. They just spent 70 years pretending they didn't. But the pretending became harder to sustain as the experiments got more pointed, because starting in 2019, physicists began running experiments that didn't just confirm the observer effect. They tested what happens when two observers disagree about reality itself. The setup goes back to Wagner's 1961 thought experiment. You have a friend inside a sealed lab. The friend measures a quantum system and gets a definite result. From the friend's perspective, the system has collapsed. The friend knows the answer. But from your perspective outside the lab, quantum mechanics says the entire lab, friend included, is still in a superposition. The friend's measurement hasn't collapsed anything from your point of view. You and your friend have contradictory descriptions of reality, and both descriptions are allowed by the formalism. For almost 60 years, this was just a thought experiment. Nobody could actually test it. But in September of 2019, Massimiliano Proietti and Alessandro Federici led a team at Heriot-Watt University in Edinburgh that pulled it off. They built a 6-photon experiment using 3 pairs of entangled photons. Optical fusion gates simulated 2 friends performing measurements, while 2 Wigners observed from outside. The experiment was fiendishly difficult. 6-photon entanglement is at the absolute edge of what current technology can achieve. The result, a Bell-type inequality, was violated by 5 standard deviations. 5 sigma. That's the gold standard in physics for declaring a result real. And what the result means is that you cannot simultaneously maintain 3 things: that measurement outcomes are observer-independent facts, that the laws of physics are local, and that experimenters have free choice. At least one of those 3 assumptions has to go. Think about what each option costs you. If measurement outcomes aren't observer-independent, then there is no objective reality. My fact and your fact can contradict each other, and both can be correct. This isn't a metaphor. This isn't a philosophical abstraction. This is what the experiment shows. 2 observers, looking at the same physical system, getting contradictory results, and both results being correct according to the laws of physics. If you find that hard to accept, you're in good company. Most physicists find it hard to accept too. But the alternative is giving up locality or free choice, and those are even harder pills to swallow. If physics isn't local, then influences can travel faster than light, violating Einstein's special relativity, the most thoroughly confirmed framework in all of physics. And if experimenters don't have free choice, then superdeterminism is true, and the entire enterprise of experimental science is on shaky ground, because you can never be sure your experimental choices aren't being manipulated by the same deterministic process you're trying to study. A year later, in 2020, Kokwei Bong and Howard Wiseman at Griffith University in Australia pushed even further. They derived something called local friendliness inequalities, which are mathematically stronger than Bell inequalities. These new inequalities can be violated even in situations where Bell inequalities are not, and their experiment violated local friendliness by more than 7 standard deviations. The implication of the Griffith experiment is stark. They showed that at least one of 3 assumptions must be false. No superdeterminism, meaning experimenters can choose freely. Locality, meaning no faster than light influences. And absoluteness of observed events, meaning every measurement has a single definite outcome that is the same for all observers. The experiments are telling us something. They're telling us that the common sense picture of reality, the one where things have definite properties, whether anyone is looking and everyone agrees on what those properties are, cannot be maintained in light of quantum mechanics. Something in our everyday picture of the world is wrong, and the experiments are starting to narrow down what it is. But if you're going to take the observer effect seriously, if you're going to accept that observation might play a fundamental role in physics, you immediately run into a different problem. How do you talk about this without sounding like a new age guru. This is a real issue, and it's one of the reasons the physics community has been so reluctant to engage with these questions publicly, because the moment you say the observer affects reality, you open the door to every pseudo-scientific claim that has ever attached itself to quantum mechanics. And there is a long, embarrassing history of exactly that happening. The most notorious example is the 2004 film, What the Bleep Do We Know? It grossed $11 million at the box office and was, for many people, their first introduction to quantum mechanics. The film featured physicists and researchers discussing how quantum mechanics proves that consciousness creates reality, that you can heal your body with your thoughts, that water crystals change shape based on the emotions of nearby humans. It mixed genuine physics with baffling claims, and most audience members had no way to tell which was which. One of the film's featured interviewees was a woman named J.Z. Knight, who claimed to channel a 35,000-year-old warrior spirit named Ramtha. The film was later revealed to have been produced, directed, and largely funded by students of the Ramtha School of Enlightenment. It was not a documentary. It was a recruitment tool for a spiritual movement, dressed up in the language of quantum physics. And it wasn't alone. The book The Secret, published in 2006, invoked quantum mechanics to justify the law of attraction, the idea that positive thoughts attract positive outcomes through some kind of universal vibration. Deepak Chopra has built a career translating quantum mechanics into self-help, claiming that consciousness can influence healing and aging at the quantum level. Entire industries have sprung up around quantum healing, quantum manifestation, quantum meditation. None of them have any connection to the actual science, but they all borrow its vocabulary, and they all benefit from the genuine strangeness of a quantum mechanics to make their claims sound more plausible than they are. This is what physicists are afraid of, not the genuine philosophical implications of quantum mechanics, but the tidal wave of nonsense that floods in the moment you crack the door open. Murray Gell-Mann, who won the Nobel Prize for his work on quarks, coined the term quantum flapdoodle for this kind of pseudoscience. Lawrence Krauss offered a useful heuristic. Be wary whenever you hear quantum mechanics connects you with the universe. Brian Cox was more blunt. Ask for the mathematics. If there isn't any, it's rubbish. And they're right to be cautious. The gap between quantum mechanics suggests that observation plays a fundamental role in physics, and you can manifest a parking space by thinking positively is enormous. The first statement is supported by a century of experiments published in the most prestigious journals in science and debated by Nobel laureates. The second is nonsense. But to the casual observer, they can sound disturbingly similar. This is the tightrope that serious physicists have to walk. And for decades, many of them decided the safest approach was to simply not walk it at all. Better to say nothing about the implications of the observer effect than to risk being associated with Ramtha and healing crystals and the secret. The irony is almost painful. The real story, the genuine mystery at the heart of quantum mechanics, is far stranger and more compelling than any pseudoscience. A century after the theory was formulated, Nobel laureates cannot agree on what it says about reality. Experiments are showing that observer-independent facts may not exist. The mathematics of quantum gravity may require observers for the universe to have any complexity at all. These are facts published in Nature and Science, not claims from a 35,000-year-old spirit. And yet the fear of being confused with the nonsense has kept physicists from talking clearly about the real thing. That fear is finally starting to recede, and the shift can be traced through a remarkably clear historical arc. It's a story of how ideas go from heretical to mainstream, and it took almost 60 years. Bell's 1964 theorem was the seed. It showed that the foundational questions had experimentally testable consequences. You could actually go into a lab and measure whether quantum mechanics was truly non-local, whether hidden variables were possible, whether the observer's choices mattered. For the first time, the foundational debate wasn't just philosophy, it was physics. But for 2 decades, almost nobody paid attention. Bell's paper sat in its obscure journal, gathering dust and citations in the low single digits. Then, in 1982, Alain Aspect changed everything. Aspect was a young French physicist at the Institut d'Optique in Orsay, near Paris. When he first read Bell's paper, he was stunned that nobody had tested it properly. He went to visit Bell at CERN to discuss his plans. Bell's first question was, "Do you have a permanent position?" Aspect said yes. He was a tenured civil servant. "Good," Bell replied. "Otherwise, I wouldn't have recommended that you undertake this experiment." That's how dangerous foundations work was considered in 1975, the most important theorem in quantum mechanics. And Bell was warning people away from testing it for the sake of their careers. Aspect pushed ahead anyway. His experiment used pairs of entangled photons and, critically, included a fast switching mechanism that changed the measurement settings while the photons were in flight. This closed the locality loophole, ensuring that no signal could travel between the 2 detectors fast enough to influence the results. The experiment ran hundreds of times. The results were clear and unambiguous. Quantum mechanics violated Bell's inequality by 5 standard deviations. Local hidden variable theories were ruled out. Whatever was connecting these entangled particles, it wasn't any kind of local influence. Something stranger was going on. The result didn't resolve the foundational questions, but it proved they were real science, not just philosophy. You could test interpretations of quantum mechanics in a laboratory. The questions had teeth, but Aspect's experiment still had loopholes. The detectors weren't efficient enough to guarantee that the measured photons were a fair sample. The switching was fast, but not truly random, and the 2 detectors were close enough that, in principle, some unknown subluminal signal might have connected them. These loopholes weren't fatal, but they gave skeptics room to doubt. And in physics, room to doubt is enough. It took another 33 years to close them all. The next shift came in the 1990s and 2000s with the rise of quantum information theory. Physicists realized that the foundational weirdness of quantum mechanics, entanglement, superposition, the observer effect, could be harnessed for practical applications. Quantum computing, quantum cryptography, quantum teleportation. Suddenly, understanding what quantum mechanics means wasn't just a philosophical luxury. It had implications for technology worth billions of dollars. And as the money flowed into quantum information, the foundational questions became harder and harder to dismiss as mere philosophy. You can't build a quantum computer without understanding entanglement. You can't understand entanglement without engaging with what Bell proved. And you can't engage with what Bell proved without confronting the observer effect. The 2015 loophole-free Bell tests were a watershed moment that arrived with almost poetic timing. In a period of just a few months, 3 independent research groups on 3 different continents, using completely different experimental techniques, performed Bell tests that simultaneously closed every known loophole. In August of 2015, Ronald Hansen's team at the University of Technology in Delft, the Netherlands, entangled 2 diamond nitrogen vacancy defects separated by 1.3 kilometers. The distance was large enough to close the locality loophole with comfortable margin, and they used high-efficiency detection to simultaneously close the detection loophole. Bell's inequality was violated with a p-value of 0.039. It was the first experiment in history to close both major loopholes at once. Within weeks, Marissa Giustina and Anton Zeilinger's team in Vienna reported results using entangled photon pairs with superconducting detectors that had detection efficiency above 95%, smashing through the detection loophole. And almost simultaneously, Lyndon Schalm and colleagues at the National Institute of Standards and Technology in Boulder, Colorado, reported their own loophole-free test using a different photon source and a separation of 185 meters. All 3 experiments violated Bell's inequality. All 3 closed the major loopholes, and they'd been conducted independently, without coordination, converging on the same result from 3 different approaches. 51 years after Bell published his theorem, 25 years after Bell died, the results were unambiguous. Quantum mechanics was correct. Every prediction Bell's theorem made had been confirmed. Local realism, the idea that objects have definite properties and are only influenced by their immediate surroundings, was dead. There was nothing left to argue about experimentally. The only thing left to argue about was what it all meant. And then came the 2022 Nobel Prize. Alain Aspect, John Clauser, and Anton Zeilinger received the Nobel Prize in Physics for their experimental work on Bell inequalities and quantum entanglement. John Clauser deserves a moment here, because his story mirrors Bell's in a haunting way. Clauser was the first person to perform a Bell test back in 1972 at Berkeley, working with Stuart Friedman. He was warned by senior colleagues that the experiment was a waste of time. After publishing the results, which violated Bell's inequality and supported quantum mechanics, Clauser struggled to find a permanent academic position. He eventually left academia entirely. 50 years later, he received the call from Stockholm. This was the ultimate institutional validation. The foundational questions that had been career poison for Bohm and Bell and Everett had become Nobel Prize material. The establishment had officially reversed itself, even if it hadn't quite admitted it. David Kaiser, a physicist and historian of science at MIT, summarized the transformation. Philosophically inclined physicists have a seat at the table now, Kaiser said, in a way that they didn't in Bohm's day, nor in Bell's day. 2025 was declared the International Year of Quantum Science and Technology, marking the centenary of Heisenberg's matrix mechanics. And at the celebrations, foundational questions were not sidelined. They were central. 100 years after quantum mechanics was born, The discipline was finally acknowledging that the questions it had suppressed for decades were not only legitimate, but essential. But acknowledging the questions is not the same as answering them, and the experiments keep getting stranger. Consider what happened in Vienna in July of 2014, when Tobias Denkmar, Stefan Sponar, and Yuji Hasegawa demonstrated something called the quantum Cheshire cat. Using a neutron interferometer at the Institut Laue-Langevin in Grenoble, they showed that a neutron and its magnetic spin could be spatially separated. The neutron traveled through one path of the interferometer, while its spin traveled through the other path. They named it after Lewis Carroll's Cheshire Cat, whose grin famously persists after the cat itself has vanished. When they placed an absorber in one path, the neutron count dropped, proving the neutron body was there. When they applied a magnetic field in the other path, the interference pattern shifted, proving the spin was there. The neutron and its own property were in different places. In 2023, a three-path version of the experiment separated three properties: the particle itself, its spin, and its energy, into three different spatial locations. The neutron was here, its spin was there, its energy was somewhere else entirely. A single particle spread across space, not as a wave function, but has disconnected properties. This is not what we mean by the observer effect in the usual sense. Nobody was watching the neutron and causing it to change behavior. But the Cheshire Cat experiment reveals something equally disturbing about the nature of quantum reality. The properties we think of as belonging to objects as being intrinsic features of particles can be peeled apart and sent to different locations. A particle's spin is not attached to the particle the way a ball's color is attached to the ball. It is something more fluid, more relational, more dependent on how you set up the experiment and what you choose to measure. And this connects directly to the work on weak measurements that Yakir Aharonov, David Albert, and Lev Weidman pioneered in 1988. Their paper in Physical Review Letters had one of the most provocative titles in physics: How the result of measurement of a component of the spin of a spin, 1/2 particle, can turn out to be 100. That's not a typo. A spin 1/2 particle can only have spin values of +1/2 or -1/2. But Aharonov and colleagues showed that by performing a very gentle measurement, one that barely disturbs the quantum system, you can obtain a weak value that lies far outside the normal range. A spin of 100 for a particle whose maximum spin is 1/2. What weak measurements revealed is that the observer effect is not an all or nothing phenomenon. It is graduated. You can extract a little information from a quantum system without fully collapsing it. You can peak without completely destroying the superposition. And when you do, the results can be bizarre. Weak values outside the normal range. Properties in locations where the particle shouldn't be. A landscape of quantum behavior that only becomes visible when you look gently instead of forcefully. This changes the conversation about observation in quantum mechanics. The observer effect is not just you look and the wave function collapses. It is a spectrum. The more information you extract, the more you disturb the system. The less information you extract, the less disturbance. But the weirder the results get. The boundary between quantum and classical, between superposition and definite outcome, is not a sharp line. It is a gradient. And where you fall on that gradient depends entirely on what you choose to measure and how aggressively you choose to measure it, which brings everything full circle. Because the observer is not just relevant at the moment of measurement. The observer determines the kind of measurement, the strength of the measurement, the question being asked. And the question being asked shapes the answer that reality gives. This is what a century of quantum mechanics has revealed, piece by piece, experiment by experiment, over the objections of a professional culture that would have preferred not to know. The double-slit experiment showed that observation determines whether quantum objects behave as waves or particles. Wheeler's delayed choice experiment showed that the choice of observation can retroactively influence what the quantum object did in the past. The Wigner's Friend experiments showed that different observers can have contradictory but equally valid descriptions of the same physical event. The quantum Cheshire cat showed that properties we think of as intrinsic can be separated from the objects they belong to. Weak measurements showed that the observer effect is not binary, but continuous, a dial rather than a switch. The free will theorem showed that if the observer's choices are free, then the particle's responses must also be free. And the 2025 quantum gravity result suggested that the complexity of the universe itself may depend on the presence of observers. Each of these results, taken alone, is strange but manageable. You can find an interpretation that accommodates it. You can find a mathematical framework that handles it. You can calculate with it and move on. Physicists are very good at this. They've been doing it for 100 years, but taken together, the results form a pattern that is very difficult to avoid. And here is the pattern, stated as plainly as I can state it. The observer is not incidental to quantum mechanics. The observer is central, not consciousness specifically, perhaps, not the human mind necessarily, but observation in the broadest sense, the gathering of information, the interaction between systems, the act of one part of the universe learning about another part. That act is not a passive recording of what already exists. It is a creative act. It shapes what comes into being. And this is what physicists have been refusing to discuss. Not because they don't know. They know. The experiments are in the journals. The theorems are proven. The data is overwhelming, but the implications are so far outside the materialist framework that has dominated science for 300 years that many physicists simply cannot bring themselves to say the words out loud. The materialist assumption is that the universe is made of stuff, particles and fields and forces existing independently, obeying deterministic laws, doing their thing whether anyone is watching or not. Consciousness is an emergent property of sufficiently complex arrangements of stuff. Observation is a passive process where stuff interacts with other stuff. There is no special role for the observer because the observer is just more stuff. Quantum mechanics challenges every part of this picture. Particles don't have definite properties until observed. The observer's choices affect outcomes. Reality may not be the same for different observers. The universe's complexity may require observers. Free will may be built into the laws of nature, and the materialist framework, the one where everything is just stuff doing stuff, cannot accommodate these results without contortion. This doesn't mean materialism is wrong. It means it's incomplete, and recognizing that incompleteness is not a retreat from science. It is the next step in science. The history of physics is a history of discovering that our assumptions about reality were too narrow. Newton assumed space and time were absolute. Einstein showed they weren't. Everyone assumed the universe was static. Hubble showed it was expanding. Physicists assumed the vacuum was empty. Quantum field theory showed it was teeming with virtual particles. Every major advance in physics has come from identifying an assumption we didn't know we were making and showing that reality is stranger than we assumed. The observer effect may be pointing us toward the next such revolution. The assumption that reality exists independently of observation, that the universe is out there doing its thing regardless of whether anyone is looking, may be the next assumption to fall. Not because of mysticism or New Age thinking, because of experiments, because of theorems, because of data published in the most rigorous journals in the world by the most careful scientists alive. And perhaps the most remarkable thing about this story is how it ends, or rather, how it doesn't. In January of 2025, a team in Vienna fired a nanoparticle of 7,000 sodium atoms through an interferometer and watched it behave as a wave. 170,000 Daltons, the mass of a small virus, existing in two places at once. And then, the moment they tried to observe which path it took, the wave pattern vanished and the particle appeared in just one place. Nobody knows why. Nobody knows what observation means in this context. Nobody knows whether the particle had a definite path before the measurement, or whether the measurement created the path. Nobody knows whether consciousness matters, or whether the complexity of the universe depends on there being observers, or whether the past is fixed before the present observes it. Nobody knows whether your decision to measure one thing rather than another is a free choice or was determined 14 billion years ago. What we know is what the experiments show, and what the experiments show is that the observer is not a passive spectator. The observer is part of the show, maybe the most important part. 100 years ago, the founders of quantum mechanics glimpsed this truth and argued about what it meant. 50 years ago, Bell proved the arguments had experimental teeth. 30 years ago, the physics community started paying attention. Today, the experiments are more precise, the theorems are more powerful, and the evidence is more compelling than ever. And the most honest thing a physicist can tell you is that we still don't know what it means. We just know that it's real. Wheeler had a phrase for this. He called it the Great Smoky Dragon. You can see the tail, which is the photon entering the apparatus. You can see the mouth, which is the photon hitting the detector. But the body of the dragon, what happens in between, is hidden in smoke. You cannot observe it without changing it. You cannot describe it without choosing a description. The dragon exists. The smoke is real. But the shape of the dragon depends on the observer. It always has, and it always will. The question is not whether the observer matters. A century of physics has settled that. The question is what kind of universe we live in if the observer matters this much. That question is still open, and the fact that it took this long for physics to admit it was worth asking may be the most revealing part of the story. Because the observer effect doesn't just have implications for physics, it has implications for us, for what we are, for what reality is, for whether the act of paying attention to the world is itself a creative act. The physicists who first saw this who first felt the weight of what quantum mechanics was saying, tried to tell us. Some of them were punished for it. Some of them were ignored. Some of them were broken. But the experiments kept coming. And the results kept pointing the same way. And eventually, even a culture built on silence had to start listening. There is a detail about the 2025 Nature survey that I haven't mentioned yet, and it might be the most important number in this entire story. 15,000 physicists were contacted. More than 1,100 responded. That means over 13,000 physicists who use quantum mechanics professionally, who solve the equations and build the experiments and publish the papers, chose not to answer a survey about what their own theory means. Some were too busy. Some didn't see the email. But some, almost certainly, didn't respond because they didn't know what to say, or because they'd never thought about it seriously, or because they'd been trained for their entire careers not to think about it. 85% of those who did respond agreed that interpretive work is valuable. That's an overwhelming consensus, but it raises an uncomfortable question. If 85% of physicists think the foundational questions matter, why did it take 100 years for the discipline to start asking them openly? Why did Bohm have to be exiled? Why did Bell have to work on foundations as a hobby? Why did Everett have to leave physics entirely? The answer is that professional consensus and professional culture are different things. You can believe questions are important while simultaneously recognizing that pursuing them will hurt your career. You can think foundations matter while publishing another paper on applications, because that's what gets you tenure. The system selects for behavior, not belief. And the behavior it selected for decades, was silence. The damage this silence caused extends beyond the three famous cases. There is no way to know how many brilliant young physicists wanted to work on foundations and chose not to because they saw what happened to those who did. There is no way to know how many insights were never pursued, how many papers were never written, how many ideas were never explored. The opportunity cost of the shut up and calculate era is invisible and incalculable. It is measured in the ideas that don't exist, the questions that were never asked, the science that was never done. What we can measure is how much the landscape has changed since the suppression began to lift. The field of quantum foundations barely existed as a discipline before the 1990s. Today, it has its own journals, its own conferences, its own career tracks. The Perimeter Institute in Waterloo, Canada, was founded in 1999 and made foundational physics a core mission. The 2022 Nobel Prize for Bell test experiments was the ultimate signal that the establishment had come around. And the experiments that have emerged since the culture shifted, the Wigner Friend tests, the quantum Cheshire cat, the cosmic Bell tests, the 2025 quantum gravity results. These are experiments that could not have been conceived, much less funded and published, in the culture that destroyed Bohm. But the shift has not been complete. Even now, there is a residual discomfort in the physics community about certain implications. You can publish a paper about quantum information theory and nobody blinks. You can publish a paper about entanglement and win a Nobel Prize. But if you publish a paper suggesting that consciousness plays a role in quantum mechanics, the response is different. Not the outright hostility of the 1950s, but something more subtle. a raised eyebrow, a polite skepticism that shades into dismissal, the sense that you have crossed an invisible line from physics into philosophy, and that crossing that line, while no longer career-ending, is still vaguely disreputable. This is why the 2022 Chalmers and McQueen paper was so careful in its language. They didn't say consciousness collapse is correct. They said it's a research program worth exploring. That phrase is doing an enormous amount of work. It is asking for permission to investigate. And the fact that a philosopher of Chalmers' stature felt the need to ask for permission tells you everything about the lingering culture. The irony is that the experimental evidence has been getting harder and harder to explain without giving the observer a central role. The Wigner Friend experiments show that observer-independent facts may not exist. The quantum gravity's results suggest observers are necessary for the universe to have structure. Wheeler, Ravelli, and the Q BISTs all place the observer at the heart of their frameworks. And yet the word consciousness remains radioactive. You can say observer. You can say measurement. You can say information gathering system. But consciousness, the one thing that every observer actually has, the one feature that distinguishes your experience of measurement from a thermometer's, that word you still have to handle with extreme care. Some of this caution is justified. The history of quantum woo, from what the bleep to the secret, to every Instagram post that uses quantum as a synonym for magical, means that responsible physicists have good reason to be precise about language. When Stapp says consciousness plays a role in quantum mechanics, he is making a specific technical claim within a well-defined mathematical framework. When a self-help guru says consciousness creates your reality, they are using the same words to mean something completely different. And the public, understandably, often cannot tell the difference. But the fear of being misunderstood has had a cost. It has prevented physicists from communicating clearly about what the experiments are actually showing. It has created a vacuum that pseudoscience has been happy to fill, and it has left the public with a distorted picture in which quantum mechanics is either too weird to understand, too mathematical to be relevant, or so mystical that anything goes. None of those pictures is accurate. The truth is more interesting and more demanding than any of them. The truth is that quantum mechanics is the most precisely tested theory in the history of science, confirmed to more than 10 significant figures, and that after 100 years, the people who understand it best still cannot agree on what it says about the world. The truth is that experiments are showing with increasing precision and decreasing wiggle room that the observer plays a role that cannot be explained away by decoherence or hidden variables or any purely mechanical account of measurement. The truth is that three of the most promising interpretive frameworks in physics, Wheeler's participatory universe, Ravelli's relational quantum mechanics, and cubism, all place the observer at the center, not as a quirk or an approximation, but as a fundamental feature of reality. And the truth is that the one escape route from this conclusion, superdeterminism, requires accepting that every event in the history of the universe was fixed at the Big Bang, that free will is an illusion, and that the correlations observed in quantum experiments were pre-programmed by initial conditions 7.8 billion years before the experiments were conducted. These are the options. That's it. Either the observer matters in some deep and not yet understood way, or the entire universe is a clockwork mechanism, and your experience of making free choices is a hallucination produced by predetermined physics. There is no comfortable middle ground. Every interpretation of quantum mechanics requires abandoning some piece of our common sense. Picture of reality, and the piece you choose to abandon determines the kind of universe you believe you live in. This is what physicists have been refusing to discuss. Not because they don't understand the options, they understand them better than anyone, but because every option is uncomfortable. And in a professional culture that prizes rigor and consensus, admitting that you don't know, that the most fundamental theory in physics doesn't tell you what kind of universe you're living in, is an admission that feels like failure. It's not failure, it's honesty. And it's the kind of honesty that physics needs more of. Because here is what a century of quantum mechanics has actually shown us, stripped of evasion and academic hedging and professional caution. We live in a universe where the act of observation is not passive, where particles do not have definite properties until they are measured, where the choice of what to measure affects the outcome, where the past may not be fixed until the present observes it, where different observers can have contradictory descriptions of the same event, where the complexity of reality itself may require observers to exist, and where the only way to avoid these conclusions is to accept that everything, including your reading of this sentence, was determined 14 billion years ago. Those are not comfortable conclusions, but they are where the evidence points, and the physicists who first glimpsed them, who first felt the weight of what quantum mechanics was telling us about the nature of reality, paid an enormous price for saying so. Bohm was exiled, Bell was marginalized, Everett was broken. Wigner retreated from his own ideas under social pressure. Wheeler waited decades to say what he believed, and the culture that punished them has only recently, and only partially, admitted that they were asking the right questions all along. The observer effect is not a laboratory curiosity. It is not a weird quirk of subatomic physics that doesn't apply to the real world. Every atom in your body, all 7 billion of them, more atoms than there are stars in the observable universe, is governed by quantum mechanics. Every chemical bond holding your DNA together, every electron flowing through your neurons as you process these words, every photon hitting your retina right now, all of it operates according to a theory that says the act of observation is not passive, that measurement creates outcomes, that the universe and the observer are entangled in ways we are only beginning to understand. It is a clue, maybe the most important clue physics has ever uncovered. A clue about the relationship between the thing that observes and the thing that is observed, between consciousness and matter, between the universe and the minds that exist within it. For 100 years, that clue has been sitting in the equations. The founders of quantum mechanics saw it. Some of them tried to follow where it led. Most of the discipline looked away. And the universe, patient as always, kept producing the same results, experiment after experiment, decade after decade, waiting for someone to take them seriously. The waiting may finally be over, but the hardest part hasn't started yet, because acknowledging the question is one thing, answering it is another. And the answer, when it comes, may require us to rethink not just physics, but what it means to exist in a universe where existence and observation cannot be untangled. Wheeler, who thought about these things longer and more deeply than almost anyone, left us with one image that captures both the mystery and the promise. He called the universe a self-excited circuit, a loop where physics produces observers, and observers produce meaning, and meaning produces physics. A universe that is not a machine running independently of its inhabitants, but a participatory act, a cosmic conversation between reality and the minds that arise within it. The universe gives birth to consciousness, Wheeler said, and consciousness gives meaning to the universe. Whether that's literally true or merely poetic, whether consciousness is the answer or just part of the question, whether the observer effect will be explained by physics we haven't discovered yet, or whether it will require us to expand our definition of physics itself, nobody knows. Not yet. But the experiments keep coming. The data keeps accumulating. And the silence is breaking. 100 years late, but breaking.